there are lots of ways that the polar versus non-polar nature of molecules has an effect on the macro-sized properties of materials. There's lots and lots of ways that it can affect the way a molecule interacts with the stuff around it. One of the biggest ways, one of the biggest things that we are used to interacting with that is determined by the polar versus non-polar nature of a molecule is the solubility of one molecule with another molecule. So the ability of one thing to dissolve something else is really determined by how polar or how non-polar that molecule and the other molecule are. And the general rule for these things are if you have two molecules that have similar polarities or non-polarities, depending on what the molecule is, that they will dissolve in one another. So the general rule here is like dissolves like. If you have two polar things, they will probably dissolve in one another. So sodium chloride, which is exceedingly polar, it is actually completely charged. You have full charges on all of the particles in sodium chloride. That will dissolve in water really well because water is very polar. It doesn't have a full charge like the sodium chloride does, but it is very polar. On the other hand, CCl4, the molecule we saw in the previous video that was nonpolar, that is not going to dissolve in water because it is nonpolar. So the carbon tetrachloride, if you try to mix it with water instead, you will just get one liquid sitting on top of another liquid. They just will not mix at all. On the other hand, if you take CCl4 and mix it with hexane, then they will. They will mix together because they're both nonpolar. This is the basis of the classic, water and grease don't mix saying. It's because water is polar and grease is nonpolar. So this then does beg the question of how soap works. The answer is that soap is a molecule that looks something like this. This is usually how soap is portrayed, where you have what we call a polar head group that is usually negatively charged. It could be positively charged. Just depends on the type of molecule that you're using, but usually you have a negative group here. So you have a big polar group at the end of the molecule, and that is attached to a bunch of nonpolar, a big nonpolar section of the molecule. So this is usually like carbon and hydrogen bonds of some kind. So you have a polar head group, and then a nonpolar tail. This is what it's usually called. And so this actually allows it to interact with both. So soap is able to clean your hands because it can interact with stuff that is polar and stuff that is nonpolar, which means that this nonpolar tail will grab the grease and stuff like that, and then the polar head group gets grabbed by the water as you're rinsing your hands and drags the grease away. And that is how soap works, or one method anyway. There's multiple methods. Like this is not going to actually disinfect your hands necessarily. So if you have disinfectant soap, then you have some other stuff that's going on as well. But just to get greasy stuff off your hands, this is how soaps work. All right, let's talk about the last topic here for this class, hybridization. So VSEPR, we discussed that a couple videos ago. This does a remarkable job of predicting molecular shape. However, we need to discuss what exactly is a covalent bond. So valence bond theory, is a method that you can use to describe how covalent bonds are formed. And covalent bond theory says that atoms create covalent bonds by sharing electrons with overlapping atomic orbitals. So you have atomic orbitals like the s, p, d, f orbitals we talked about in chapter 6. You have electrons in those orbitals. We have one atom with its atomic orbitals comes up close to another atom with its atomic orbitals. They overlap, and that overlapping of the orbitals is where they share electrons. The question then becomes, how the heck do we get those shapes that we saw? the trigonal planar, the tetrahedral shapes, I mean, for that sake, the trigonal bipyramidal shape, that weird one. How do we get those shapes? From atomic orbitals. Because if you remember, those atomic orbitals were almost exclusively either on the axes or, 45 degrees off of the axes. Like, they were very, very orderly. There was an orderly arrangement of those atomic orbitals, and they didn't have these weird 120, 109.5 degree angles. And the answer to this is you can't. You can't get those shapes using purely atomic orbitals. And so what was discovered, before I get to that, another thing that was an issue with taking pure atomic orbitals and getting those covalent bonds that we were seeing is that carbon is very well known to bond 4 times. But if you actually look at its electron configuration, if you go through and you work out where all the electrons are sitting in carbon, it only has 2 unpaired electrons. So if it only has 2 unpaired electrons, how is it forming 4 bonds? It should need an unpaired electron for each of those. So, in order to get the right geometries and the correct number of unpaired electrons, it was discovered that when we're forming bonds, we're not actually just taking pure atomic orbitals and matching those up from one atom to another. Instead, what's happening is we are getting what's called hybridized orbitals. And we get these hybridized orbitals by literally adding atomic orbitals together. We take the wave functions that describe different atomic orbitals, and when we add those wave functions together, we get different wave functions that actually work better. Now, before we actually take a look at what those, the 3D shapes of those orbitals, when we're figuring out how many hybridized orbitals we need and how many atomic orbitals we need to make those, it's pretty straightforward. If you take 3 atomic orbitals and you add their wave functions together, what you get out the other side is another 3 orbitals. So however many atomic orbitals you mix, you're going to get the same number of hybridized orbitals. So that makes it pretty easy to figure out, how many things do I need attached to my central atom? That's how many hybridized orbitals I need. So if, for example, we have this here, boron trichloride, which looks something like this, and the boron is breaking the octet rule here, it needs 3 things attached to the central atom, so we need 3 hybrid orbitals. And so we are going to need 3 atomic orbitals to make those hybrid orbitals. Just for every bonding group and electron group attached, we need 1 hybrid orbital in this new bonding scheme that we're talking about here. Now notice here, I said for every bonding group. So for something like CO2, I don't need 4 hybrid orbitals for the carbon here. I just need 2, because this is a bonding group and this is a bonding group. So for this particular molecule, I would need 2 hybrid orbitals, because I have 2 bonding groups. So however many things you have attached to the central atom, regardless of whether they are bonding groups or lone pairs, you need 1 hybrid orbital for each of them. And so when we're creating these hybrid orbitals, we are just going to start with the lowest energy atomic orbital that we have, which is the s. So remember, we have s, p, d, and f atomic orbitals. We're just going to start with the lowest energy one, stick that in there and use that, and then as we need more, we will go to higher energy ones. So for example, if we were naming the kind of hybridized orbital that we make for a molecule that is AB2 in terms of its classification from what we saw earlier. So it has 2 things attached to the central atom. If we have 2 things attached to the central atom, then we need 2 atomic orbitals to make our hybrid orbitals. So we're going to use the s. We only have one of those, because remember the s subshell only has one orbital, and so we're going to need one p orbital as well. So this particular molecule that has two things attached to the central atom, we are going to call sp hybridized. And that's it. It's no more complicated than that. If we have three things attached to the central atom, we're going to take the lowest energy first again, so we're going to take the s. We still have two more things that need hybrid orbitals. If you remember, we have 3 orbitals in p, 5 in d, 4, sorry, not 14. We have 14 electrons that can go into F, but 7 orbitals in F. We're never going to get up to the F, by the way. So we have 1, 3, 5, 7. So we're going to take the 1s and then 2 p orbitals. And actually, let me make sure I have that notation correct. Yeah, okay. Sometimes I forget if it should be an exponent or a subscript. But it is correct to be an exponent there. So this is sp2 hybridized. And this is going to be the same. Because again, we have 3 things attached to the central atom. To get the shape we need, we're going to hybridize 3 atomic orbitals. And we always start with the lowest energy and just work our way up. And so we don't care that one of those is a lone pair. Same thing is going to be true here, only now we have 4. So this will be sp3. We've now used all of the p atomic orbitals. This is sp3 hybridized. That's what we call this. And so are all the rest of these here. Because all of these have 4 groups. 4 groups on that central atom. If we go up to 5 groups, because we've lost, or not lost, but we've used up all of our p orbitals, now we're going to have sp3d. So we're going to take one of those d orbitals. And again, we're just taking all these atomic orbitals and we are literally adding their wave functions together. And as we'll see in a minute, we get new wave functions as a result. And then the last one here, sp3d2. And that is as high as we're going to go. So we have 6 different atomic orbitals that we are adding together to give us 6 new hybridized orbitals. And these new hybridized orbitals are going to be equivalent. They're all going to have the same overall shape, but they're obviously going to be pointed in different directions. So here we have sp hybridized orbitals. Take an s orbital, a p orbital, add those together, and what you get is kind of a mix between the two. So we have these 2 orbitals as a result, and when you overlap those, they look like this. And this matches perfectly with what we see. So like CO2, carbon dioxide, is sp hybridized, and it is linear. And what we get from adding an s orbital and a p orbital together is 2 new hybridized orbitals that are 180 degrees apart from each other. Same type of thing here with sp, where we have 3, so sp2 hybridized orbitals. Take the s orbital, 2 p orbitals, add those together. That gives us 3 new hybridized orbitals that are all 120 degrees apart, which matches perfectly with our trigonal planar via CPR shapes. So hopefully you can see here these shapes, having a sphere, having the lobes here on 90 degrees away from each other, this would never give us trigonal planar geometries. But when we take those and get new orbitals, we do get the 120-degree geometries. Similarly here with sp3, so now we've used up all of our p orbitals here. We get 4 new hybridized orbitals that are 109.5 degrees away from each other, just like tetrahedral shapes. And so we don't have a big slide for the other two here, but trigonal bipyramidal, same thing. Throw in a d orbital there, and you get this odd shape that we saw with trigonal bipyramidal molecules. And then throw in another d, and you get the octahedral shapes. And so this works really, really well with predicting how those molecules are going to bond together. So then just to finish this up here, how do multiple bonds fit into this? Because we were ignoring the fact that we had double or triple bonds in things like CO2, where we had this double bond here, but we only gave that, why did I put no there? That's weird. So we only gave it one hybridized bond. If you go back here and look at that, we said, you know, we have a double bond to oxygen, but there's only one bond here. Where'd that second bond come from? Well, the second bond actually did come from the atomic orbitals. So when we have hybridized orbitals that exist between the two nuclei here, this is going to give us an opportunity to then have a second bond that is using those atomic orbitals, but that second bond is going to exist in a different plane from the other ones. Not a different plane of existence, but a different plane, like literally, geometrically, a different plane. So if we had, so let's say this is the carbon here, and this is the oxygen over here, and it would have another one off to this side, but it is going to have a single bond that exists here directly between the two atoms, and then the second bond is this interaction here that is above and below that single bond. And so the two bonds exist between the two atoms, just in different spaces. They're occupying different places. So we're not hybridizing all of the orbitals here, and so the ones that are left unhybridized can still participate in bonds. They're still there to make double bonds. And as we'll see in a second, triple bonds. So these bonds that exist above and below the plane of the nucleus, so this would be the plane between the nuclei here, these bonds that exist above and below that are called pi bonds. And then the bonds that exist directly between the nuclei, which is what we see here, these are what we call sigma bonds. And so like I was trying to show you there a second ago, so we have the pi bonds above and below, sigma bonds directly in between. If we're going to go up, actually before we get to triple bonds, one really significant thing about pi bonds relative to sigma bonds is that sigma bonds are able to rotate. So here in this particular molecule we have two chlorines that are attached to two different carbons. And those chlorines don't really like being near each other. They like to be on opposite sides of the molecule. And so this molecule will actually allow rotation around this bond here. And so this chlorine is actually going to move to get as far away from this chlorine as possible. And sigma bonds will allow that to happen. Sigma bonds allow rotation around the bonds. Pi bonds, on the other hand, do not. Pi bonds, because you have to have an overlap between these two atomic orbitals, they can't rotate. Because if you rotate this bond, well then they're not overlapping anymore, and you've broken the bond. And so pi bonds essentially lock the molecule into a particular shape. And so you actually will have two different molecules for this molecule versus this one. So this molecule is different than this one. This is what we would call, let's see, that would be, well, it says 1,2-dichloroethene, but actually that should be cis 1,2-dichloroethene. and then this would be trans 1,2-dichloroethene. Because here, the two chlorines are on the same side, and here they are on opposite sides. And so we actually do have to specify that, because those are going to have slightly different properties, and they're not allowed to move because of that double bond. So the difference between pi and sigma bonds is actually significant. All right, do I have? No, I don't. Okay, so just real quickly here, before I end the video for today and for the class, if you're wondering, okay, triple bonds, how do those come into play? Well, we do have one last region of space where there's a way we could fit in an extra bond here. So we have a bond that exists below, above and below the plane right here. But if you think about it, we could also fit another bond, another pi bond, coming directly out of the screen towards you and back away. So we would have essentially completely surrounded, we've completely filled in this space in here with electron density. So we have above and below here, coming directly out, going directly back, and then directly in between the two atoms. And so we can't really fit any more electron density into that space there. That is as full as it can get. Technically speaking, it is possible to have a quadruple bond. It is extraordinarily rare, though. You have to have very specialized metal bonds that are happening, and we are not worrying about metal bonds in this class. So for our purposes, we will never have anything bigger than a triple bond. All right, that is pretty much it. The last couple slides here are just talking generally about the sp3d orbitals and sp3d2 orbitals and the angles that exist there. But I'm not too worried about that because we've really covered most of this already. So that is it. Congratulations, you have made it to the end of General Chemistry 1. Give yourself a pat on the back. If you have someone near you, tell them to pat you on the back. You deserve it. So, be sure to be working on the homework. Get that done as quickly as you can while this stuff is fresh in your mind. And I will talk to you all the next time we get together.